at Northeastern on the topic of programmable, AI-driven, and virtualized next-generation cellular networks. And hopefully, in the course of this talk and discussion, we'll give a more precise meaning to all of these terms. And all right, so I think we're all aware of what are some of the limitations of current existing cellular system, 4G, 5G systems. They're all based on a monolithic architectures, and they're hardware-based. So all the networking functionalities from baseband processing up to higher layers of the protocol stack are intertwined into the hardware fabric. They're not separable from the hardware fabric. And as a consequence, the devices have limited programmability, if any. This makes it hard to update the functionalities, improve them, reconfigure, optimize the functionalities. And also it leads to the well-known problem that is, it's been discussed extensively in the industry, the so-called vendor lock-in, right? So all the hardware, especially at the radio access network, needs to come from the same from the same vendor, right? And you can have interoperability between different vendors. It makes it very hard to programmatically control a network, right? So to define the behavior of a network and to redefine the behavior of a network, especially when we're trying to do it at a large scale, right? With deployments that include hundreds of devices or base stations. This leads to a lot of manual reconfiguration. We need to deploy engineers that will manually reconfigure the network in many ways. And it leads to an increasing gap between what we know in theory, right? We know a lot about how to optimize networks in different situations, and what we can actually do in real deployments, right? There's a growing gap between the knowledge base that the community has about how to optimize networks and what you can actually do. All right. I believe, and many believe in this world, that future cellular networks will be open in the sense that they will be based on standardized interfaces through which multiple disaggregated functions will be able to interact in the radio access network and in the core network. They will be programmable in the sense that we'll be able to define the behaviors of the network. They'll be virtualized in many ways. So a lot of the functionalities will be implemented in software on virtualized infrastructure. They will be data-driven, so they'll be able to learn how to optimize their functionalities based on what has happened in the past. They'll be autonomous in the sense that they will, based on high-level directives, be able to optimize the behavior of the network in an autonomous way. They'll be self-healing and resilient, so they'll be able to reconfigure a lot of the functionalities at the edge, at the core, and at the radio access network to be able to withstand disruptions that can be intentional or non-intentional. All right, how do we get there? There's a few things that have happened in the last few years. Some of them come from the world of wired networks, right? One of them, one big idea is the idea of software-defined networking that we're all familiar with. And in software-defined networking, I'd argue that there's two main ideas. One idea is the separation between the control plane and the data plane. Okay, and that's helpful for sure. The second idea is the idea of exposing application programming interfaces through which, on a centralized abstraction of the network, through which you can define and control the behavior of the network. Okay, and this is a powerful idea, which is a significant disruption with respect to the previous way of thinking of networks as a distributed collection of routers where we would program the behavior of each individual router. The second big idea that comes from the wired world is the idea essentially of network function virtualization, where now you have a physical infrastructure or NFV infrastructure that contains physical hardware with virtualization layers. And on top of that, with different technologies, virtual machines, Docker containers, you can instantiate atomic functionalities or components that can provide a number of different network functions that can be orchestrated and instantiated by means of orchestrators in a flexible way. Okay, now some of these ideas have been making it into the wireless world in the past few years, right? So the traditional approach is obviously to put a monolithic hardware-based base station on top of a tower. And this is, again, an immutable, hardly reconfigurable base station, right? And one thing that has happened is what is referred sometimes as vertical disaggregation, or people have been using different terms over the year, Cloud Run, etc. But the idea is that you now have a hardware base station that is an open base station that implements only some minimal functionalities, sometimes referred to also as white box base stations. And then a lot of the functionalities can be implemented in software on NFV servers, okay? Vertical disaggregation. The second thing that has been happening is what is often referred to as horizontal disaggregation, okay? So we're moving from a situation where we have all the various functionalities from physical layer up to the radio resource control functionalities, all implemented on the base station. And now these functionalities are migrating to the cloud in a sense. So they migrate to a number of different entities that are referred to in the language of cellular networks as the ORU, which is what you see here on the right, the ODU, and the OCU. These are disaggregated entities that contain some of the functionalities that are traditionally implemented in a base station. The ORU implements the low physical layer functionalities and the RF functionalities, so things like, you can think of things like beamforming, etc. The ODU implements the baseband processing functionalities and some of the lower level link layer and MAC layer functionalities. The OCU implements higher level radio resource management functionalities. And the OCU, ODU, and ORU are all connected through standardized interfaces that are being standardized by a number of different entities. The ORU is a white box hardware-based station, right? While ODU and OCU can be implemented in different ways. For example, they can be implemented as virtualized functionalities in the cloud. Now, the other aspects of what is happening in the industry is that all of these entities, the OCU, ODU, and potentially also the ORU, are being connected with so-called RICs, or RAN intelligent controllers. So these RAN intelligent controllers are entities that receive information that can observe analytics from these various different entities through standardized interfaces again, and provide a centralized abstraction through which you can implement so-called XApps. Okay, these XApps are control applications that can control the behavior of the network at the radio access. Okay, so you have the RAN intelligent controllers that are connected through standardized interfaces with these aggregated entities and they can control the behavior of these entities by observing data that is being generated by these entities. Okay, this makes networks open, cellular networks, of course. This is what we're discussing today. Open because they're based on open interfaces. Programmable because we can program their behavior through the RIC. And virtualized because a lot of the functionalities can be implemented on virtualized entities. Okay. Now, there's a number of different entities that have been promoting this aggregation and standardization. Notably, the ORAN Alliance, which is an operator-led alliance of different operators, vendors, academic institutions, etc. It's been standardizing all of the interfaces, in addition to the near real-time RIC, RAN intelligent controller, which is in charge of controlling operations that have time scales in the order of, from tens of milliseconds up to a second. and also the so-called non-real-time RIC that has to do with controlling functionalities that have slower time scales, that have to do with service management and orchestration, can be in the order of greater than 1 second. Okay. Now the vision is to go in the direction of an end-to-end programmable, virtualized, and open network, where all of the functionalities are implemented in software that can be controlled and reconfigured in real time to achieve the vision that I outlined at the beginning. As of today, a number of the entities that you see in a traditional network can be implemented in software, and often with open source software, right? From the UE, there's open source frameworks that can implement UEs, even though they're not really caught up with the latest releases, but they're going in that direction of LTE base stations, 5G base station, the software for edge cloud, the software for orchestration, slicing, core network, etc. All of these things you can find today implemented with open software, and there's a lot of work that needs to be done in integrating them and in making this software more robust. But we are certainly going in that direction. Now, obviously, when you talk about open architectures and programmability, the idea of being able to control the functionalities through advanced algorithmic developments is something that, you know, as engineers and computer scientists, we're immediately tempted to do that, and we should do that because there's a lot that can be done. So in open 5G architectures, you can control a number of functionalities with artificial intelligence that can be implemented and deployed in different parts of the network. You can think of artificial intelligence on mobile devices to do things like real-time and waveform-based adaptation on the device themselves. You can think of artificial intelligence in the radio access network to control functionalities like scheduling, mobility, and access. You can think of artificial intelligence at the edge to control optimization of the RAN, edge services and caching. You can think of AI in the core for functionalities like orchestration and slicing. Slicing obviously is across the core, the RAN and also the edge. Now, I'm going to give you a few examples of work that we've been conducting in various of these areas where we have applied artificial intelligence to programmable and open networks in different parts of the, in different components of the network. Now, when we look at the ORAN architecture I described at the beginning, right? I mentioned the fact that there's two RAN intelligent controllers that are being standardized, the near real-time RIC and the non-real-time RIC. And the idea is to develop apps, control apps that can be executed both at the near real-time RIC and at the non-real-time RIC to control functionalities with different time scales. And this is here's a few examples of the intelligent control loops that you can implement in ORAN. The ones that you see at the top are currently supported by the ORAN specifications. You can think of control loops between the non-real-time RIC and the near real-time RIC that can control functionalities like policies, slicing that include that affect in the order of thousands of devices and that have time scales in the order of several seconds or more. You can think of applications, of control applications that can control session management like handover, load balancing, etc., that have functionalities that affect hundreds of devices with time scales in the order of hundreds of milliseconds, where you would close the loop between the near real-time RIC and the CU component of the network. There's medium access management functionality where you close the loop between the near real-time RIC and the DU, right? Things like scheduling policy, run slicing, that have time scales in the order, again, from tens of milliseconds to hundreds of milliseconds, etc. And there's potentially other control loops that are sort of closer to the physical processing of data closer to physical devices that have time scales less than 10 milliseconds or in the order of even 1 milliseconds between, there would be closing the loop between data that could be generated by the RU or the mobile devices and the DU or within the mobile devices itself. These control loops will be exposed and controlled in the future. I believe they are currently not part of the ORAN specification that is primarily focusing on a little more higher level abstract functionalities with longer time scales. But I'm convinced that these functionalities will also be exposed and controllable in the future. All right, so let's just go through a few examples of how artificial intelligence in these open architectures can be leveraged to control a number of functionalities. So we've been doing work, for example, in the last few years on the problem of so-called radio frequency fingerprinting. This is work that we've done at Northeastern under sponsorship from DARPA. The idea in radio frequency fingerprinting is to be able to basically recognize devices that are identical in terms of hardware by just observing a few baseband samples. So the idea is, imagine you have two identical devices, and then of course you can, it doesn't need to be two. We've done experiments with hundreds or even thousands of devices with different levels of performance. But imagine, the basic idea of the problem is you have two different devices. They are, their hardware is nominally identical, but they're not really identical because there's manufacturing imperfections and things like that. And they're transmitting exactly the same waveform from a bit level perspective, right? So they're transmitting the same data on a wireless channel, and at the receiver you receive the signal transmitted by the two devices. You send it back to baseband, and then you feed it into a neural network that has been trained to be able to recognize the different devices based on the hardware imperfections that they cause on the radio frequency bits. And what we've seen is that during the course of this project is that neural networks can become very good at recognizing different devices. However, the wireless channel has an effect that can be, and this is something, when you apply AI to wireless problems, it's a new problem with respect to the significant amount of work that has been done on AI for computer vision, for example, right? In computer vision, channels don't vary. You don't have an external entity that is acting in a sense on your data. What we saw is that the wireless channel creates a significant disruptive effect on the ability of the convolutional neural networks to recognize the different devices. And so you have to come up with techniques to bring the performance back to where it would be without the effect of the channel. So in a sense, if you train on a certain day on channels that are seen on a certain day, and then you test on the same day, you get very accurate performance, even with large population of devices. If you train on one day and test on a different day, the performance degrades significantly, okay? So you need to develop techniques, and this is something we've been doing in the past couple of years, to remove the effect of the channel or to train the neural networks in such a way that the effect of the channel is not going to be this prominent. Another example is work that we've been doing on what we call polymorphic communications. The idea in polymorphic communication is to be able to use artificial intelligence technique, and specifically we're using convolutional neural networks, to be able to automatically detect different waveforms and reconfigure your receiver to be able to receive that waveform in real time. So imagine now you have a transmitter that is on a packet by packet basis, changing some parameter of the waveform, just because maybe it doesn't want the waveform to be that easily decodable. And so you can use, for example, different FFT sizes, different modulation schemes. The receiver, just by observing a few baseband samples, is able to infer what parameters are being used, for example, what level of FFT, and reconfigure its receiver in real time to be able to demodulate the signal itself. This is something that, you know, to be effective, it needs to be implemented in an efficient way. So we've been implementing this system on FPGA. So we have the neural networks that are implemented on FPGA so that they're able to recognize the parameters of the waveform in real time, and to do that in an energy efficient way on the device itself. And then they're able to reconfigure the receiver to be able to receive in real time the correct waveform. And implementing this in FPGA with respect to doing it on general purpose processors on the device itself or on edge cloud can lead to significant reductions, or order of magnitude reductions in energy and latency. This is a short, I don't know if, I hope you can see it. It's a short video of a demo where you have a transmitter that is alternating between different parameters of the waveform, this FFT size, and the receiver is able to recognize them in real time and reconfigure its behavior to be able to receive the information. Okay, so this is a couple of examples of applications of AI on the devices themselves, operating on very low level baseband samples to make inference and control parameters of the protocol stack in real time. Now, there's a number of applications for which you want to apply AI algorithms, both in mobile devices and at the RAN in a coordinated way, to be able to control functionalities. So an example is deep learning applied to be able to recognize 5G, to control 5G millimeter wave waveforms and networks. Millimeter wave transmissions are obviously characterized by directionality, high data rates, and blockage, and they rely on complex control procedures, specifically on beam management, which is a procedure that tries to align the beam between a transmitter and the receiver. So the way that traditionally this is done is by means of so-called beam management pilots. Okay, so pilots are transmitted periodically, and they are transmitted between bursts of data. And these pilots are used between a transmitter, think of a base station, and the receiver, to be able to find, to synchronize transmission between the beam that is used by the transmitter and the beam that is used by the receiver, right? So you want them to be aligned to be able, and there's obviously a number of different possible combinations, and synchronizing between transmitter and receiver requires time if you do it with exhaustive beam management, which, you know, leads to delays in establishing the links, especially when you're bringing up the network for the first time. Now, the way we've been trying to do it with a framework that we like to call DeepBeam is by using, again, artificial intelligence that, and again, we've been using convolutional neural networks that tries to directly coordinate between transmitter and receiver by identifying what is the angle of arrival and what is the beam that is being used by the transmitter. And by just doing that directly on data packets. So imagine now the transmitter is transmitting a data packet by using a certain beam. The receiver is able to identify by looking at a few baseband samples what is the angle of arrival that is, what is the specific beam that is being used by the transmitter, and what is the angle of arrival between that beam and the beam that is being used by the receiver. Okay, so you don't need pilots, you don't need exhaustive scan, and you can reduce the latency and the overhead. Specifically going a little bit into more detail here, what does DeepBeam learn to recognize? Basically, it's able to recognize when you have a transmitter that is using a certain beam, the receiver can be tuned to a certain beam, and it will receive a waveform from the transmitter, will send it through the neural network, and the neural network is able to say which beam is the transmitter using between the various possible beams that are in the so-called in the set of the transmitter. And the second thing is it's able to choose between a certain different set of angle of arrivals, of possible angle of arrivals between the transmitted beam and the received beam. Okay, and again, this is done by observing a bunch of IQ samples. And once you have identified the transmitter beam and the angle of arrival, the receiver can adapt its beam to align it in the best possible way to the transmitted beam. All right, and obviously, we've been doing quite a few experiments on this with 2 different millimeter wave radios. One is an analog, it's a millimeter wave radio based on the NI baseband processor and the side beam analog phase array at 60 gigahertz. We've also been collecting data with Pi Radio SDRs. This Pi Radio is a small startup that has created a digital beamforming based 60 gigahertz radio. And we've been collecting quite a bit of data, and all the data set and the code is available if you're interested in this space. Another example of applications of artificial intelligence, both at the mobile devices and at the RAN, is work that we've been doing on so-called DeepSense. DeepSense has to do with spectrum sensing and identifying unused bands on spectrum holes for both licensed and unlicensed bands. The objective is to be able, again, to use convolutional neural networks we can use to detect in real time from a few baseband samples spectrum holes and identify on large bandwidths which channels are available and which channels are not available. Okay, and then obviously this knowledge and information can be used to reconfigure the behavior of a transmitter that can be at the mobile device or at the base station. And what's promising is you can achieve significant high classification performance with real world and also with simulated data sets. And if you implement this on FPGAs, you can do that with latency that is in the order of fractions of milliseconds, so faster than the LTE subframe. So for example, in cellular networks, it can be used to reconfigure the transmission frequency on basically on a frame by frame basis. All right, continuing on our journey through the various parts of the network, been looking at work where you use artificial intelligence to reconfigure the behavior of the radio access network in sliced radio access networks. So imagine now you have radio access networks where you're implementing multiple slices. You can have a machine type traffic slice, a ultra reliable low latency slice, and a classical mobile broadband slice, right? And you want to control scheduling and potentially also the size of these slices, although this is work that we're doing now of controlling the size of the slices themselves. You want to be able to control the scheduling in real time through the near real-time rig that we discussed at the beginning, to be able to tune in an automated way the parameters of the radio access network for each individual slice. And you want to do that in a data-driven way. So you want to learn from what is happening in the network to control the policy of each individual slice. Okay, so the context that we're looking at is of a disaggregated radio access network, okay, which we discussed at the beginning. So imagine now you have your cell sites connected with the edge cloud that implements the DU and CU functionalities. All of these are connected through standardized interfaces with your near real-time rig, which will be probably located in your regional cloud and is implementing the various X apps. And then the near real-time rig is connected with a non-real-time rig, okay? So we're focusing here on the X apps, on the control applications that will control the behavior of the scheduling on the various slices. And we want to do this in a data-driven way, okay? Now, one characteristic of ORAN and the way ORAN is being defined is that you cannot run machine learning models in ORAN that have not been pre-trained, okay? So you can't just run models and hope that they will train themselves and learn how to optimize resources. You have to work with pre-trained models, okay? Because it's considered to be a safer mode of operation for production networks, obviously, than using just random models that have not been pre-trained. And you can use online learning, so the models can be refined live in real time, but the model needs to have been pre-trained. So you need to train offline, sorry, and then you can execute online. And obviously, to train models offline, to be able to realize this vision of data-driven control, you need to have a lot of data, okay? And there's very vast amounts of data. It's hard to get them because operators, for obvious reasons, don't want to share their data. And so we need what I like to call open wireless data factories, okay? And we are lucky enough at Northeastern to have test beds and devices that can help us generate vast amounts of data. One of them is the so-called Colosseum. Colosseum is basically a data center. We like to think of it as a smart RF data factory. Sorry. It's 21 racks of equipment that include the 256 programmable software radios, USRP X310. Each software radio is connected with a server and a high-performance server that can provide the virtualization environment and the computational capabilities that are necessary to control the radio. There is a large fabric of FPGAs that interconnects all of the different front ends, the 256 front ends, RF front ends in a mesh. And it is able to emulate in real time then the 65,000 channels that are created between the 256 radios. And in addition to that, we have a lot of storage capabilities, capability to synchronize at least a portion of the radios in time and frequency. And so it's a significant data center that can generate a lot of data and can provide the testing ground for algorithms like the ones that I described today. Colosseum was created by DARPA, a research agency connected with the Department of Defense in the United States to support the Spectrum Collaboration Challenge. They was trying to develop new blue sky ideas to use artificial intelligence for spectrum sharing. And after the Spectrum Collaboration Challenge, it has moved with support from the National Science Foundation, which we gratefully acknowledge, to Northeastern to be opened to the research community. So we are operating the Colosseum, we're using it for our own research, but we're also opening it up for external users. So if you're interested in using Colosseum, please let me know. All right, an example of work that we've been doing on Colosseum on RAN slicing. So we have implemented in Colosseum a scenario that represents a cellular deployment with 4 different base stations that are deployed in the actual area where the Roman Colosseum is. So we've used information of actual base stations that are implemented in that area. We've modeled the RF propagation in that area. there's some limitations on what we can model in Colosseum, but it's a pretty accurate system. It's a pretty accurate, it has pretty accurate modeling capabilities, let's say. So we have deployed 4 base stations. So the base stations are mapped to different software radios. And there is 10 UEs with different mobility patterns connected to the various base stations. So all the 40 UEs are implemented with SRS LTE software. Each one of them has 3 different slices. The slices I described at the beginning, MTC, URL, LLC, and enhanced mobile broadband slices. And then there's the 4 base stations are also implemented with SRS LTE software. Now we have used one of the initial ORAN releases, and we have significantly extended it to provide the capability to interface an SRS LTE base station with an ORAN RAN intelligent controller. So we have created the ORAN E2 termination that is run on a container. The E2 manager, E2 is the interface that connects the RAN intelligent controller with portions of the radio access network. The E2 manager and the RIC database are also implemented into containers. And then there's different containers, 1 per base station, that run the different X apps with deep reinforcement learning agents that will control the behavior of each base station. In fact, we have 1 deep reinforcement learning agent for each slice on each base station. So we have 3 slices on 4 base station, 12 different agents. These different agents are run on different containers on the RAN intelligent controller. And then there is also the non-real-time RIC that is basically providing, in our case, so we have an interface for data collection, and then we have an offline training engine and various different models that can be selected and deployed on the XApps to control the network. Okay, so this is basically an ORAN open source infrastructure that is connected with the softwareized cellular network that is implemented at scale in Colosseum. So what we've done is we have used these various deep reinforcement learning agents that have been implemented with fully connected neural networks. They're relatively small models for what we were trying to do here. They've been trained offline with 63 hours of experiments. So we ran the experiments in Colosseum. We collected the data. We used the data to train the models offline, and then we implemented the models in Colosseum to control the behavior of the different RAN slices. And specifically, we're trying to, with these 12 agents, we're trying to control for each slice the scheduling policy between round robin, water filling, and proportional fair. And then we resize periodically the slices. And as of now, in work that we're doing right now, we're also trying to determine through deep reinforcement learning agents the specific size for each slice. Okay, and as you would expect, by doing this, we're able to achieve pretty good performance. We're able, with respect to using fixed scheduling policy, we're able to increase, in this scenario, the spectral efficiency by up to 20%. We can guarantee the performance of the more delay-sensitive slices and reduce the buffer occupancy in the RLC in downlink by 20% in average. Okay, so we've talked about AI in the radio access network. Now, the next step, in a sense, is applying AI to control the edge. This is work that it's, in a sense, it's ongoing. We have been doing, we had some work that we presented at last year's MobiHawk that tries to control slicing at the edge. And the idea is, in typical slicing work, The emphasis has been on assignment of resources for communication. So basically assigning for the radio access network different resource blocks at various base stations to provide the resources needed to isolate a certain slice of traffic. We've been looking at it from the perspective of both communication, storage, and computational resources. So imagine you want to provision a certain service. For example, you want to have video streaming applications that may require significant storage and they may require significant computational capabilities. How do you deploy slices in the network, and how you reconfigure the slices that can provide all the networking, storage, and computational resources, considering the coupling across the various resources with respect to only considering communication functionalities. All right, and maybe the last thing that I wanted to mention here, and this is, as you will see, something that is not yet specifically related with AI algorithms, but it's it has to do with the aspect of programmability that we touched upon at the beginning, right? So we've been talking quite a bit about open interfaces, disaggregation, algorithmic control of various functionalities, but programmability is a slightly different concept in the sense that you want to be able to provide abstractions, in a sense, that let you change the behavior of the network when conditions change, because maybe you have a different commercial objective or something else has changed in the operational requirements of your network. Okay, so we've been developing something we like to call CellOS. And CellOS is what we like to think of as an intent-based and data-driven network operating system. So the objective is to do some of the things that we've been discussing today, where you close the loop between data is generated by the network and control actions that need to be taken to recontrol the network. But do that at a higher level of abstraction, in a sense. We define the behavior that we want to achieve at a high level, and the network automatically determines what are the control actions that need to be taken in different parts of the network to obtain that behavior and objective. Okay, so imagine something like you have an operator intent that is expressed at a high level, like I want to be able to stream 4K video to 100 users in Times Square, New York, from 8 p.m. to 9 p.m. Okay, so what you need to do today is to deploy an engineering team that will mess with the software, in the assumption that the hardware will allow you to do that, and manually reconfigure your network to obtain that. With CellOS, the idea would be to provide automated software generation, recognize at a high level the behavior, decompose the behavior to obtain the different control actions that need to be taken, and generate the software that can take those control actions in real time, and to provide zero-touch reconfiguration of the network to obtain the objective that we express at a high level. Okay, this is the vision for CellOS. We have an initial version of CellOS that was published last year that is looking at a subset of the problems that we would like to solve to enable that vision. The idea is to provide network abstractions that will hide some of the lower level details and hide the distributed implementation and the distributed nature of the optimization problem, and do this in a distributed way. There's a number of challenges to be able to do that. First of all, what is the right way to abstract the underlying network topology, right? Do we want to have a distributed or a centralized abstraction? Ideally, we want to expose a centralized abstraction, but then we want the control actions that will reconfigure our network to be taken in a distributed way. how do we automatically generate the optimization programs that will be based on the different runtime parameters? How do we perform cross-layer optimization? How do we comply with the strict requirements in terms of timing, etc.? So at a glance, CellOS, you can think of it as follows. An operator wants to define at a high level what is the specific objective for a certain slice in the network, right? So you want, for example, a certain slice to provide the maximum rate behavior, want to minimize the power, or something like that. There is an optimization framework where based on a network abstraction that is exposed by means of APIs, the optimization framework generates an abstract representation of the network control problems that you're dealing with, and then it automatically decomposes the network control problems into different distributed control problems that are then sent to the various components that need to be controlled. Okay, so the idea is you define the behavior on a centralized abstraction. There is an automated generation of distributed control programs that control the various base stations, the various softwareized base stations on the network. And then these are executed in a distributed way close to network state. Okay, I'm gonna skip some of the details of the integration with ORAN, but the overall idea, just going into a little more detail, for each individual slice, the operator can define the specific behavior to be obtained. This is expressed in a high-level language. Imagine something in the order of 10 lines of code, where you express the actual utility function that you want to obtain for a certain slice. Specific constraints, for example, you can give constraints on minimum data rate for certain users or other constraints that you can think of. And then the specific, you can specify within the system some specific algorithms that you want to use for decomposing, for decomposition of the actual problem. Now, there is an entity, sorry, there is an entity that receives information from the actual deployed system to provide an abstract representation of the network. And it receives also the desired behavior expressed at a high level. And then this generates an abstract representation of the problem, and then it decomposes it in an automated way. So it basically creates distributed algorithms that can then be sent to the system, can be dispatched to the system to control the behavior of the softwareized run. This is CellOS in a nutshell. In the current version that we've published of CellOS, this abstract representation and problem decomposition, this happens based on notions from nonlinear optimization. There is basically, we're using classical decomposition techniques to decompose centralized nonlinear optimization problems. And then we're generating the algorithms, obviously, depending on the specific problem that we're looking at. In some cases, the distributed decomposition will lead to optimal solutions. In other cases, the solution will be suboptimal. There is no magic here. And then we generate these control programs that will control the softwareized run that is then executed on a reconfigurable protocol stack, like SRSLT or OpenAir interface. Okay, so what I'd like to emphasize is that you can basically obtain different network behaviors by just modifying a few lines of code. So in your high-level definition, you change the specific objective function, and you can reconfigure the behavior of the entire network or the entire slice. And the other thing I wanted to emphasize is that, without a framework like CellOS, if you want to obtain a behavior like this, you need to explicitly model the optimization problem that you're trying to obtain, right? With CellOS, you do that at a very high level of abstraction where you specify the objective function and some of the constraints, and the system takes care of generating the abstract representation for you and of decomposing it to obtain the distributed algorithm that will control the behavior. Okay, so there is an automated generation of the distributed control problems. Now we've prototyped CellOS on a couple of different run prototypes on open air interface and SRS LTE. We use the test beds with 3 base stations transmitting over the air and connected with 9 different cell phones. This has been implemented in the arena testbed that we have at Northeastern. It's basically imagine there's 64 antennas that are deployed in an indoor space. These antennas are connected with, by means of coaxial cables, to software-defined radios, and the software-defined radios have a bunch of servers that can instantiate the virtualized protocol stacks. Okay, so we've used specific base stations, specific antennas in this deployment as base stations, and we've used off-the-shelf phones to connect to the base stations. We've looked at various different scenarios. I'm going to show a couple of results from scenarios with high interference. So imagine a crowded deployment with pico and femtocells. You can, with respect to standard implementations of open air interface, you can get with CellOS significant throughput gains in a scenario like that. And I think, if you ask me, okay, the most interesting thing is that not only you can achieve optimized behaviors, but you have the flexibility to switch between different objectives, right? So you can now instead switch to an objective that tries to obtain a lower power consumption, and you can reduce your power consumption 10 times with respect to a standard open air interface implementation. And you can do that continuously, right? So depending on how you define your objectives and you configure your system, you can move between throughput gain, energy efficiency gain, fairness gain, and so on. And the other thing that I'd like to mention is you can do that on a slice by slice basis, right? So you can have different slices that are coexisting exactly on the same hardware, and you can reconfigure the different slices to obtain different behavior. So you can have a slice that is maximizing rate and a slice that is minimizing power. And last thing is that this has been implemented also on the PAWR testbed. I'm going to talk about this in the last 5 minutes of my talk. But basically, PAWR is a large-scale deployment in Salt Lake City as part of the Platforms for Advanced Wireless Research program. And the fun thing about virtualization is that you can take containers that have been used for experiments in our arena indoor testbed or on Colosseum and deployment on different base stations with long-range setups like in PAWR, and deploy them on networks where you have base stations connected with UEs that are hundreds of meters apart, and still obtain all the good results that you have with CellOS. Last thing I wanted to mention about CellOS is that we're working on a new version of CellOS where we don't explicitly use mathematical models for the distributed generation of optimization programs, but where everything is based on deep reinforcement learning agents. And we're gonna basically try and evaluate what is the performance gain, if any, that we can get from data-driven control with respect to model-driven control that we've been using so far. So we talked quite a bit about data, and I'd like to conclude by saying a couple of things about data that is needed to generate the next generation of data-driven technologies. I've been lucky enough to work on the Platforms Advanced Wireless Research Program, which is a program spearheaded by the National Science Foundation that is trying to create 4 city-scale platforms for advanced wireless research in collaboration with an industry consortium that includes a lot of the the industry players in the operators, manufacturing, and computing continuum. PAWR has so far awarded 3 grants to create programmable testbeds at the scale of small portions of a city. The PAWR testbed is being deployed in Salt Lake City, and that's been used in some of the experiments that I showed earlier. It's a programmable software-defined cellular networks with massive MIMO components. It's up and running for experiments. I invite you to take a look at the website if you're interested, led by the University of Utah. Cosmos is a testbed that is being deployed in West Harlem, New York, led by Rutgers, University, Columbia, and NYU. And it's focusing primarily on millimeter wave communications as well as programmable optical backhauls. The AirPow platform is focusing primarily on unmanned aerial vehicles, drones, so to speak, and mobility, and is being deployed in Raleigh, North Carolina. So PAWR and Cosmos are already available as of today. AirPow will be generally available soon. And there is a rural broadband platform that will be announced very soon. It's been delayed a little bit by COVID, but it's something that will be announced in a matter of weeks at this point. It's already been selected. And then complemented by this is the Colosseum, which is the, we talked about it, is the world's largest simulator located at Northeastern. So all of these platforms are programmable and available for the community to play with. So I'd like to just conclude by saying a couple of things. One is that with virtualization and these programmable platforms, we can do a lot of interesting things. Like, with containers, we can test at scale on emulated scenarios, validate in real wireless environments, and then test at scale on the various platforms that are available through the community. And the other thing that we can do is to generate large amounts of data on one platform, and then use the models that have been trained based on this data and use them on different environments to generalize, extend, and test at scale. To conclude, I think I gave you an overview of a lot of work that has been conducted in this area. I believe that future wireless systems will be open, programmable, virtualized, data-driven, autonomous, and self-healing. I hope I gave you a good sense of what each of these terms means in this context. I gave you a little bit of an overview of work that we've been doing to go into this direction. There's a lot to be done, and I think we are lucky enough to be in an era of renaissance for wireless, and where the intersection between wireless computation and algorithmic development is becoming extremely exciting. It's opening up a lot of opportunities for research, for commercial deployments, and I very much invite you all to take a look at this area, because there is a lot to be done. Thank you all. Glad to answer any questions.
All right, thank you very much, Tommaso. Excellent presentation and very impressive facility and research having done there. So now we are open the floor for questions. Please feel free to type your questions in the chat window, or you can just unmute yourself and ask a question directly.
Thank you for that excellent talk. I have a quick question. So in CellOS, right, you said you're currently using a standard optimization and you want to explore using a DRL, right? So can you say that what do you expect DRL to be better than classical optimization approach?
I certainly hope so. Look, so there is clearly depends, right? So there's specific optimization problems for which we know how to obtain an optimal solution in a distributed way, okay? So in that case, we know how to get to the optimum. Now the question is, are the models that we're using to model the problem accurate enough that when we achieve theoretical optimality, that's really optimal from a system perspective? That's the question in those cases. For other problems, our decomposition it's sort of it's a local best effort or something like that, and so we don't know how to theoretically achieve the optimum, right? So for those situations, it's absolutely possible we might be doing much better with DRL. It's hard to predict in general, but that is certainly something worth exploring.
Great, thank you very much.
Yeah, thank you for the discussion, the question. So next, Sajal.
Hey, Tommaso, good morning. How are you?
Sajal.
Hey, great talk. Great talk. Good to see you. So a couple of questions. So one is, you did not talk much on the security aspect, right? So that's one question. And the second question is that it's an excellent test bed, excellent setup, excellent research. What are the killer applications that you think which will be stress test for this type of platforms?
Yeah, these are great questions, Sajal. In fact, on the security side, there's clearly a lot of interest, a lot of geopolitical discussions and the like, right? The U.S. government is extremely interested in security. I'm going to look at it from the perspective of open radio access networks, right? So if we move in the direction of open radio access networks, there's a clear advantage on one side in the sense that the level of reconfigurability that we bring to bear, right, enables us to make networks resilient in terms of specific disruptions or attacks, right? You attack my radio access network that is implemented in a certain area, I can very likely I can reinstantiate in a different point and do that in a matter of milliseconds, probably, okay? And with minimal disruption. Now, on the flip side, you are introducing, you're certainly expanding with radio access, with open radio access networks, you're expanding the surface threat, the threat surface, I should say. You are introducing new interfaces. All of these interfaces can be attacked. And it's not clear that as of now, security of these interfaces has been a major concern in the design. You are introducing models and algorithms that can be attacked in various different ways. For example, you could, there is a well-known attack, there is the so-called data poisoning attack. You're using machine learning models. If the data that is used to train the models has been tampered with, then your algorithm may not behave in the right way. So there's a number of different aspects that need to be investigated, and that's, I think, so good news for researchers. There's a lot of opportunities to do research, and we're only at the beginning of that. Now, as far as the killer applications, that's always, we have to sort of wear our magician's hat to try and predict the future. I think, clearly virtual reality and augmented reality and extended reality, all these things will play a role for sure. And I'm not thinking about video games for the most part, but I think more about enabling people to meet in virtual spaces. I'm sure that's something that we can all relate with during this last year and a half. I'm not sure that we all want to go there, but that's something that will be happening, and I think that these technologies will play an important role there.
Thanks.
Thanks, Ajal.
Thanks, Tommaso. I have a just follow-up question regarding the security side, right? I think you discussed a few excellent aspects about security, and during your presentation, you talk a lot about AI, and we have been seeing a lot of attacks towards AI models, the backdoors, AEs. It seems that this is a very exciting research at its intersection between AI and wireless. But at the same time, AI is kind of fast evolving, right? The security problem has not been fully addressed. So what do you think about the risk of integrating AI extensively, in the wireless network, and especially if we push it into the industry products?
Right. And I think this, the way I see it is that this will be happening for sure. I mean, the whole industry, the whole IT industry, but also the whole wireless networking industry is going into that direction. And so you are absolutely right that we're just scratching the surface on in terms of looking at this secure AI problems, but we'd better do it, because it will be happening. I think it's a matter of time.
Yes, I absolutely agree. And I see Claudio raised the hand. So Claudio, go ahead.
Thank you. Hi, Tommaso.
Good to see you, Claudio.
Traditionally, the telco industry has been lagging behind the cloud computing industry by, I don't know, like 5 to 10 years, I would say. And as a matter of fact, they have been using virtualization and containers for a long time, while the telco industry only right now has been starting using those technologies. In my opinion, I think that the telco industry is accelerating its pace. So what is your opinion? Do you agree on this feeling? And if yes, do you think there will come a time when the telco industry will be able to move at the same pace as the cloud computing industry?
Right. I think these are great questions, Claudio. I agree with you that the telco industry is accelerating. I also, the telco industry is also changing. And it's expanding in many different ways, right? So there's companies and operators that were not part of the telco ecosystem. Think Microsoft, Google, but also Amazon. And there's others that are becoming, they're investing significantly on 5G. They're investing significant amounts of money on these technologies. They're investing in network automation. Why is that happening? Well, there's a number of different reasons. Some of them are purely geopolitical, right? There's been geopolitical competition in the area of 5G. The geopolitical competition has seen the US at a certain point, it was felt by many that the US was lagging behind, and the answer to that was to accelerate in the area where the US excels, which is in the world of software, algorithms, virtualization, etc. So I think that's a little bit of what we're seeing now. The Open RAN ecosystem favors favors ecosystems that have multiple players with respect to monolithic giants, and it supposedly favors innovation in this space. So that's the bet in a sense. And if you if you observe how the different governments have been positioning themselves with respect to these technologies, you see, I think, a lot of the answers with respect to what we're discussing.
Great, thank you, Tommaso. And I think Vijay wants to ask another question. Go ahead, Vijay.
Hello, Dr. Melodia. Very nice presentation.
Thanks, Vijay.
I have a couple of questions. You mentioned about intelligence. I am also a firm believer that it will happen, but there are several issues with that. For example, one of the issues I could think of, let's say if you train your model in Blacksburg, which is a rural region, and you try to apply any other place, it will not work. Or even if you train it now and suddenly a building is raised up and then the whole channel model has gone in the sea, right? So how do you see, and if there is no scalability of the solution that you develop, like the model-driven approaches, then there is no way you can use it in a widespread manner, right? And the following this, the next question is, would you make your this ORAN code open source anytime sooner?
Yeah, so there's a couple of questions folded there. On making this open source, we're gonna be making parts of this software open source pretty soon, especially models can be used to do experimentation in Colosseum. There's a few things that we'll make open source this month. In terms of deploying, generalizing models so that they can be executed in different environments and that they can, obtain the performance that you wish for in different environments. I think this is a great question, and that's what I was trying to allude to at the end when we was talking about, deploying containers in different environments, right? That's the only way to learn about how these things will generalize is to try to train the models with large amounts of data and then try to deploy them in different environments with specific characteristics and benchmark them against various versus environments with different characteristics. We're just at the beginning of all of this. And I think as a community, we need to come up with standardized data sets. We need to come up with large scale testing platforms, and we need to come up with specific benchmarks to which we can say, hey, this model works better than this other model in these scenarios. We're not there yet. So.
Thank you.
Yes, absolutely. I think that's a great point. If we look at the machine learning community, that grows so fast in the past decade. The primary reason is they have the large standardized data sets, and also it's simple to use, right? It's it's made available to the entire research community, and also plus those machine learning platforms developed by a couple of leading companies that have been really useful. So that's definitely the way to go.
I agree, and I mean, maybe some machine learning in the audience might kill me, but some of the problems that we're dealing with are harder than computer vision problems, where they have their data sets and
absolutely
here the number of parameters, the number of things that we're trying to control and recognize. It's a big problem, and we've started later than they have. So
right. And I cannot agree more. Their data set is so simple, right? An image and a label. And in our system, there are so many parameters. I totally agree. And that makes it a lot more complicated. And we are quickly approaching the end of this session. There are a lot more questions I'm sure we want to discuss. But thank you very much, Tommaso. Excellent presentation. Wonderful visions. And I'm sure there will be follow-up questions sent to you, and check your email box. And if we receive any additional emails, we'll definitely forward to you. And on behalf of all the audience, yes, and also the conference, thank you very much for the wonderful presentation.
Thank you. I'd like to thank you all again for inviting me. It's been a pleasure here, and glad to answer additional questions.
Thank you very much, Tommaso. So with that, we end this session. Have a break, and then we will come back to the technical session again. All right, we'll see you in a short while.
Ciao, Tommaso. Hey, hon, how are you?
Great, great.
Wonderful, wonderful.
Okay, we have a 15 minutes break. We will use the same Zoom link for the next session, but we will start at 15:30.